The topic for this afternoon will be the ecology of desert dirt, which I hope you will find more interesting than you think. I'm Dan Gruber. I'm a steward with the McDowell Sonoran Conservancy. Given where we are in Scottsdale, I assume that most of you know about the McDowell Sonoran Preserve, which begins just a few miles away from here. The preserve is a natural open desert space. It's the largest urban preserve in the country. The McDowell Sonoran Conservancy is the organization whose people help take care of the preserve and do many other things. You may know that the city of Scottsdale actually owns the preserve. The Conservancy partners with the city to study and maintain and support the preserve in a variety of ways. The Conservancy focuses on science, doing research about the best way to manage open space, education, like this afternoon, and of course, stewardship. But in addition to taking care of the land and the people who come to visit the preserve, we also use the preserve as a living laboratory and do a lot of research in it in order to determine best management practices for maintaining that kind of space. And many of our educational offerings, which you can find on the Conservancy's website, are actually offered in the preserve, which is a wonderful experience, being able to see live whatever it is we're talking about. The Conservancy, of course, is a nonprofit, and so we welcome all support, whether it's volunteer hours to become a steward, or financial support, or in-kind, or whatever. Whatever it is, we'll take it with gratitude. Okay, now let's turn to the topic at hand. I want to start with a question for you. When you go out into the desert, whether it's in the preserve or a neighborhood park, or perhaps even your neighborhood, what are the things that you notice? What are the things that get your attention when you're out there? Or you're using your phone the whole time and don't pay any attention at all? Sharon? Okay.
Beautiful boulder formations and things like that. Brown's Ranch, I may look at some of the trees and the plants and stop and smell the creosote bushes and stuff like that.
Okay. Particularly notable rock formations, trees. I'm sure many people, of course, notice saguaro, especially if they're big and interesting ones. In the spring, I imagine we pay attention to the flowers and stuff like that. And that's what all of us tend to pay attention to when we're out in the desert. But now I'm going to show you some pictures, and I'd like you to look at each picture for a few seconds and think about the question that's at the top of each of these slides, okay? So what really covers the desert?
Dirt. Yeah.
Dirt. Pardon me?
The former mountaintops.
Former mountaintops in the form of dirt. I mean, there's more. What the desert really is covered with is rock, the dirt that rock turns into, and the soil that dirt may turn into if it's augmented and structured. There's more of this out in the natural desert than any species of plant. And in some places, there's more rock, dirt, and soil than there is all the plants that you can see. And the reason we're going to talk about it this afternoon is, first of all, there's so much of it and we pay so little attention to it. But more important than that is that this stuff is literally and figuratively the foundation for the entire ecosystem. Everything that lives here depends on rock, dirt, and soil, and a few other factors that actually are formed through the same kinds of geological processes that form rock, dirt, and soil. So this is the environment to which everything has to adapt in order to live successfully in this ecosystem. And it behooves us, if we want to understand the ecosystem, to understand something about this key component of the environment. Okay, so what we're going to talk about today, the ecology of desert dirt. And this diagram summarizes the transition from rock to dirt, and then the transition from dirt with the addition of some different material and some structuring into soil. Now, one thing I want to point out on this chart, we're going to talk more about it later, and it's going to come up again and again and again, is the role of some key transportation mechanisms in distributing resources globally. And the main mechanism that's really important in this regard is wind. Jet stream and other large-scale wind phenomena that redistribute resources, mostly in the form of dust, globally. You may remember a few years ago, there was great concern about, quote, toxic dust blowing here from Africa or from China. I mean, transoceanic transportation of material. You're going to see this again and again today, and it's a crucial factor in shaping ecosystems globally. It's one of those mechanisms that's at work on a global basis. Biota? The question is, what are biota? Biota are all living things. It's plants, animals, us, microbes, everything that's alive, assuming we can tell. Okay, let's start with the first step of the process, how rock gets converted into dirt. The process of breaking rock apart is called weathering. And there are three kinds of weathering, and mostly they all take place at or near the surface. There's chemical weathering, which is chemical reactions between oxygen in the air, and particularly water, and the minerals in rock. And these chemical reactions can result in minerals in the rock dissolving or splitting apart, and other things as well. But for that to happen, obviously the rock, which usually forms deep underground, has to be close enough to the surface so that the air and water can get to it. There's physical weathering, and the thing that probably you're most familiar with, since most of us came from someplace colder, is the freeze-thaw cycle. And water is a really interesting substance. It has the very unusual property that when it freezes, it actually expands, which is why icebergs float on the ocean. They're actually less dense, they're lighter than the water, than the liquid water is. So at or near the surface, liquid water gets into cracks in the rock. If that water freezes, it expands and acts like a hydraulic wedge that's widening and deepening existing cracks in the rock. And then the ice melts, turns back into water, it shrinks, but the crack doesn't shrink. The next time it rains or whatever, more water fills up the crack. It freezes again, expands the crack further and deeper. So freeze thaw and related processes are physical weathering. And then finally, near the surface, there's biological weathering, things like plant roots getting into little cracks in the rock. Plant roots, when they absorb water, expand. So just like freeze thaw, they act kind of like little hydraulic wedges that widen cracks. We often use the word erosion to actually mean weathering. Erosion, in fact, describes the processes by which weathered material, fragmented rock, is transported from one place to another. The most common form of erosion, of course, is gravity. I mean, a piece of rock breaks off high up on a hillside, down it comes thanks to gravity. But wind and water obviously can also transport material. So there's weathering, break the rock apart, and erosion to move it, to move the broken rock someplace else.
Are lichens weathering? Do lichens sort of destroy some of the rock surface, or?
Yeah, lichen is the question was, is lichen weathering a form of weathering? And absolutely. There's another talk that I do, as a matter of fact, called Desert Surfaces, that talks extensively about lichen. But lichen, the fungal component of lichen, have little tiny, they're called hyphae. They're not roots exactly, but they're little fingers of fungal material that get into crevices in the rock and expand when wet. They do the same thing that roots do. So lichen often are the beginning of the breakdown of the surface of rock. And the next thing you'll see growing on the rock is moss, something a little bigger, a little more robust. Okay, there's a problem with these processes, though, that is obvious if you think about it for a minute. I'm sure everybody's been to the Grand Canyon, or if you haven't, you've seen pictures of it. So there's these gigantic, very visible layers of rock, right? And they extend for miles along the canyon. And of course, you know they extend for miles into the bedrock to the north and south of the canyon as well. So we have this enormous mass of the same kind of rock. If any of you have been to Central Australia, you probably made a stop at Ayers Rock, called Uluru in the indigenous language. Ayers Rock is a granite monolith. It's a single granite boulder about 3 miles across. Yosemite, El Capitan, Half Dome, other enormous granite monoliths. These are single rocks. Rock usually forms deep underground. And almost always the rock that forms deep underground forms as one solid, huge mass of rock. Here's a very typical way that some of the rock in the Northern Preserve was formed. A big bubble of magma, molten rock, liquid rock, bubbles up from the deep interior of the earth. But it gets stuck someplace way underground, many miles below the surface. It can't make it to the surface as a volcano. And over thousands of years, it may cool and solidify. And what started as liquid molten rock turns into solid granite rock deep underground. That's how Ayers Rock was formed, how Yosemite and the Sierras were formed. So we have these enormous expanses of rock deep underground. Well, when I was talking about weathering near the surface, I kept saying, you know, this gets into the crack and that gets into the crack and expands it. Well, wait a minute. How do I go from having this enormous miles wide solid hunk of rock into having a bunch of cracks? Where did the cracks come from? Well, it turns out there are several ways to crack enormous hunks of solid rock, and processes that actually can go on starting deep underground. The importance of the cracks is, and I take This was once a solid piece of rock before I hit it with a hammer in my yard. What the importance of cracks generally, and this is another ecological mechanism that you're going to hear about again and again, is a crack exposes more surface area of the rock to all those weathering processes. As you can imagine, although rocks do change very, very slowly over millions of years, on a short-term basis, there's nothing much going on in the middle of a rock. Surfaces are where almost all of the action in nature takes place. It's where physical, chemical, and biological actions occur. So surfaces are good, and the more surfaces I have, the better it is for change to occur, biological and ecological change. So cracks are really important. The question is, how do they get formed in solid rock? And there's a couple of ways. One way is tectonic forces, geological processes, deep underground. The rock generally forms way down, way below ground. And you may recall that the center of the Earth is extremely hot. In fact, the center of the Earth is about the same temperature as the surface of the sun. And it gets hotter the deeper into the Earth you go. You've probably seen pictures over the years of miners working in really deep mines, just covered with sweat because it's 150 degrees down there. Well, deeper down, it's so hot that real rock that's formed, like magma that's cooled into granite, isn't yet completely solid and brittle. It actually is bendable. And geologic forces can cause hunks of rock deep underground to bend or fold. And you can imagine that the rock that's on the top of a bend or a fold gets stretched, and it can actually begin to split apart, just like cookie dough or something, if you were to manipulate it. And by the way, here's a picture, lest you think I'm making up the idea that rocks can bend. This is at the surface. You can see that these are tiny. This is only about 10 feet of rock, but you can see clearly that it's been bent. And someday, if I see you out at the Gateway Trailhead in the preserve, I'll show you in the mountains of the preserve a giant fold of rock. It's all the same rock, and it can be literally traced over miles, and it goes through a bend, and then it goes way up and it bends again. So this really does happen, and it creates cracks in rock. There's another way to produce a bunch of cracks in a huge mass of rock, and it has to do with the fact, again, that the rock generally forms deep underground. So we're going to do a little bit of arithmetic. Anybody remember what the air pressure is at the surface of the Earth? 14.7 pounds per square inch. That's the pressure of the atmosphere. See, somebody paid attention in high school, for God's sake. Scuba diver, okay. Okay, so if you're a scuba diver, so what happens to the pressure every 33 feet you go down? Right. And the reason why 33 feet of water adds another 14.7 pounds per square inch of pressure is the weight of the water, the weight of 33 feet of water. Okay, let's imagine a hunk of rock, a huge hunk of granite that's solidified from magma 20 miles down. It's under a lot of pressure from the weight of 20 miles of rock above it. In fact, a little calculation with some assumptions says that the pressure 20 miles down is about 70 tons per square inch. That's 140,000 pounds per square inch versus 14.7 pounds per square inch at the surface. So call the surface pressure 0, 140,000 pounds per square inch. Okay, now everything down there is under the same pressure. And because the things down there are stable, that means there has to be internal pressure balancing external pressure on everything. So magma wells up from deep in the earth, 20 miles gets stuck. The magma is under 70 tons per square inch of pressure. So it has an internal pressure of 70 tons per square inch. As it forces its way through the rock around it, that's pressing in on it with 70 tons per square inch of pressure. The magma solidifies into granite. The granite has an internal pressure of 70 tons per square inch, just like everything else down there. So now, okay, here's the situation. The granite's down here, 70 tons per square inch of internal pressure, balancing 70 tons per square inch of external pressure from 20 miles of material above it and all the material around it and so forth. Over millions of years, often, not always, often, rocks that started out deep underground end up, of course, on the surface. And how did they get there? Well, two main factors are at work. First of all, tectonic forces again may in fact be pushing that rock toward the surface. There are all kinds of processes that can cause that to happen, that could move huge masses of rock around underground, including toward the surface. At the same time, everything at the surface is weathering and being eroded away. And so over time, what may happen, doesn't always happen, is that the rock underground is being pushed up as the surface above it is being weathered away until eventually the rock reaches the surface. Okay. Think about the pressure now. Rock forms down here. Internal pressure 70 tons per square inch to balance 70 tons per square inch from all the stuff above it. And now the rock gets pushed up while the surface gets eroded away, which means that the rock isn't as far below the surface over time, and there's not as much stuff on top of it over time, which means the pressure from all the stuff on top of it over time is going down as the rock and the surface get closer together. But the rock still has 70 tons per square inch of internal pressure, even when it reaches the surface where the external pressure is 0. What do you suppose happens to the rock as it rises toward the surface? Yeah, the rock expands. Solid rock expands because of its internal pressure becoming greater than the external pressure pressing on it. You've seen this many times, you know, in documentaries and newsreels, right? Helium balloons, big weather balloons filled up on the ground, and there's a bubble of helium, but the bag is mostly empty. And then you see a picture of the balloon at 100,000 feet, and the bag is completely filled because the helium gas, which was under pressure when it was filled on the ground, as the external pressure diminishes as the balloon goes up, the gas expands. Solid rock does the same thing, and that causes a myriad of cracks in the rock. And the reason I'm spending so much time on these processes is because without these processes, you know, Ayers rock is still one giant piece of rock, even though it's been on the surface for hundreds of thousands of years, because it doesn't have very many cracks in it. And without cracks, all those weathering processes, there's not, the surface area is minimized by not having cracks. And so all those weathering processes happen much more slowly than if it was full of cracks. Well, here are ways to produce lots of cracks. Okay, so we now have cracked rock, thank goodness. And weathering can occur as the rock gets close to the surface. By far the most active source of weathering is water. I'm going to show you, I'm going to start an experiment now that we'll come back to later to talk about surface area and why it's so important. These are 2 glasses of water, and this is just tap water from the drinking fountain outside. And these 2 glasses have roughly the same amount of water in them. And I have here a beef bouillon cube. Can you see that? A beef bouillon cube. And a packet of, this is ramen, a packet of beef flavored stuff from a ramen packet. And it turns out these actually have very nearly the same amount of material in them, okay? So what I'm going to do is I'm going to take the bouillon cube and drop it into the glass of water. And I'm going to take the packet of beef flavoring, if I can get it open. Let's see if it's open. No, it's not open yet. Tear it a different way. There we go. Okay. So I've put the packet of beef flavored powder into this glass, and we'll just let them sit for a while and come back to them later. Okay, you'll see the importance of surface area. So the cracked rock gets exposed to water near the surface, all those weathering mechanisms can begin. And that process, by the way, continues even at the surface, of course. I mean, freeze thaw, obviously. But another factor, second mention, wind-borne dust being blown in. Most of what's in dust are really fine, tiny, tiny particles of minerals that generically usually are clay kind of minerals. And that implies a certain class of minerals, but very common component of wind-borne dust, because the particles are so fine and so light, they can be carried for thousands of miles by the wind. So dust accumulates in cracks in the rock, just like water does. Well, clay has a couple of interesting properties when it gets wet. As many of you probably know from working with it, it gets slippery. It also expands when it gets wet. So clay particles accumulating in cracks in the rock, when they get wet, act kind of like water accumulating in cracks when it freezes. In other words, it expands and acts like a hydraulic wedge, widening and deepening cracks. So water and dust, as well as roots and everything else, continue the process of weathering below the surface and at the surface. This is an aside. How many of you have noticed orange rocks as you go hiking? You're all spread out, so you have to pass this around. You see orange rocks, especially alongside trails or roads, dirt roads that have been, plowed. So what do you think? What's the orange? It's not spray paint. So what is it? What do you think the orange color is? Iron oxide, AKA Rust. Okay, yes. What you're looking at is rusted rock. And the reason is that there is a tiny bit of iron in our rocks, in many, many rocks, but certainly our rocks locally, much less than 1%, but over thousands of years of exposure to oxygen and water, that tiny bit of iron that's exposed at the surface reacts with the oxygen in air or water and forms iron oxide, ferric or ferrous oxide, and rusts. And I mean, if you saw that color on a piece of metal, you would know immediately what it is. Well, it's the same thing. Usually, the orange side is down. It's the part that's in the ground. And the reason is that the ground stays wet longer than the top of the rock does when it rains. So the rock that's sitting in the ground is exposed to water for longer than the upper portions of the rock over thousands of years. The bottoms of rocks preferentially rust faster and to a greater extent than the tops do. So often we don't see the orange, but when we build a trail or a road, guess what we do? We push rocks aside and we often turn them over. And this, by the way, is a real picture from alongside a trail in the preserve. There are areas like this that are just covered with nice orange rocks. Okay, so we've got dirt now. We've gone through all the mechanisms that turn rock, huge masses of rock, into dirt ranging from boulders to very, very, very fine-grained clay particles, AKA dust. So now let's talk about how we get from dirt to soil, which is not quite as obvious. Soil is absolutely based on, ultimately, the bedrock in the area and the dirt that the bedrock fragments into, but it also reflects the addition of other material. The material can be local, but the biota, the living things, particularly plants growing in an area, of course, they grow, they die, they decay, and as they decay, all of their chemicals go back into the soil. But also we have stuff brought in on wind and rain, and that will be all kinds of nutrients and elements that may or may not exist in the local dirt. So this dirt gets augmented by this additional material. And then over time, it actually can structure. One of the characteristics of soil is that it has a structure, as we'll talk about, and turn into soil. Okay. So the key is we tend to use dirt and soil interchangeably. They're not. Soil's absolutely based on dirt. Soil is not dirt. Things grow on dirt, but a lot more things grow on soil because of the nutrients and some other characteristics that soil has and dirt doesn't have. This is sort of an ideal cross-section of well-developed soil. It's got, of course, rock and dirt at the bottom, and then it's got a series of layers that are called horizons. And there's a calcic horizon, an argillic horizon. Usually there is a horizon of organic material, which is the dead plants, but there are alternatives, which we'll talk about a little later. This is a cross-section of really well-developed soil. This happens not to be here. This is a road cut, I think in the upper Midwest, but it's an area that's considered semi-arid. And from here down, this medium brown or tan layer is dirt, okay? I think you can just barely see that there's a whitish layer on top of it, at least whitish material in there. That's the calcic layer. This orange to dark brown expanse is the argillic layer, and it gets darker as we get toward the surface, because lying right on top of everything here is a thick layer of dead and decaying organic matter that comes from the plants that are growing. And so as the plants die and decay, in this layer, the nutrients and elements in that decaying plant material work their way down into the layer right below, which is the argillic horizon. Okay. There won't be a quiz. Okay, let's start with the calcic horizon. It's called the calcic horizon because it is full of calcium, specifically calcium carbonate, which is the same material that makes up our bones and coral reefs and limestone. Calcium carbonate, which is calcium combined with carbon dioxide in the air, accumulates in this layer. And over tens of thousands of years, what starts out as little specks of calcium carbonate, which is white, can form solid layers, usually about a meter, 3 or 4 feet below the surface. And those layers can be really thick, layers of solid calcium carbonate. And we have a name for that, an affectionate name. Do you recall what that name is? It's caliche, right? The bane of people building houses, digging pools, trying to trench, sometimes even making a garden if it's close to the surface, because when it gets really thick, it's rock and it's solid. And when it gets, when a caliche layer in the calcic horizon of soil gets thick enough, it does something really interesting. It forms, in effect, a waterproof lining underneath the soil above it. Now, that doesn't matter for many of our native plants, which are succulents and have shallow root systems that right near the surface. You know, having 3 or 4 feet of soil is more than sufficient. But for our bigger plants, particularly our trees, which usually have some kind of taproot, mesquite particularly, you know, having a deep taproot, they've got to work their way, those roots, by expanding and contracting and exploiting tiny cracks in the caliche, have to work their way through it to get to whatever's down below. So it's a real issue. A well-developed calcic layer is a marker for aridity, for desert or semi-arid regions. If you travel anywhere in the world and you see a nice, well-developed layer of white, hard rock exposed in a road cut or in any kind of a ditch, sometimes at the surface, the odds are you're in an arid or semi-arid region. And the reason is evaporation. We'll talk a little bit more about that later. The question here, it happens that calcium is rather common in our dirt here, our rock, our dirt, and therefore our soil. But you find this horizon in places that have no calcium locally at all. So where do you think it's coming from? It's windborne dust. Windborne dust redistributes nutrients and elements globally. Things that are common in one place, if they're fine enough to be picked up by the wind and carried high enough so they can be transported over distances, you know, the stuff that's common here can be transported dozens or hundreds or thousands of miles away and deposited someplace else where it may or may not be common. Here it happens to be common. Other places it's not common, but calcium is available almost globally. And in arid regions, it forms the calcic horizon. And here are some samples of caliche. The one sample here is kind of the beginnings of a caliche deposit. You can see the white specks that have been deposited on this hunk of granite that's beginning to build up into a solid layer. And this is solid caliche, a tiny piece from my house. I've got everything at my house.
And
Hmm?
Did I misunderstand? I thought most of our caliche was as a result of water coming in, the little lakes and ocean stuff dries out, comes back in whatever it was, 8 or 10 times, and the salts were what?
It's not. That might have been a source millions of years ago, but it goes on regularly just with rainwater. It's happening all the time. The question is, was the caliche formed by oceanic deposits that waxed and waned in Arizona over millions of years ago? And yes, probably it's not a salt, but there was calcium deposited, but it's still going on now, just rainwater, and we'll talk about it.
So is the carbon coming from organic plants or is it?
It's coming from the atmosphere. It's carbon dioxide from the atmosphere. The calcium is reacting with carbon dioxide from the atmosphere to form the carbonate. Typically not the carbon coming from the decayed plant material. Okay, let's go up a layer to the argillic horizon. That name comes from the Latin word argilla, which means clay.
Just one more thing. So if it's coming from that layer, then does that process stop when you get the organic layers above it?
No, the question is, did the process of forming the calcic layer stop when the organic layers formed above it? The answer is no, and I'll explain why in a bit. So thank you for leading. It's a good leading question. But let's talk for a bit about the argillic, the clay-rich environment. What's really important about this layer is that it's composed primarily of extremely small particles of clay-y material, clay-like material. Clay is a generic term for a whole family of related minerals. Very, very fine particles. And what's key about this layer is it has an enormous amount of surface area. Remember surface area? The reason surface area is important is because it's where everything in nature happens. So having a lot of surface area in this layer means you can have biological reactions, you can have chemical reactions, water gets stored there by capillary action, air gets trapped there between these tiny particles. Now, I've talked a lot about surface area, and now I'm making the claim that because this layer is made up of extremely small particles, it's got enormous surface area, and that's really, really important ecologically. By the way, those particles, guess where they came from? Windborne dust. This is all primarily dust. Okay, we're going to do some more arithmetic. So this is a cube, and this cube is 5 by 5 by 5 units. Doesn't matter what the units are. So it's 5 by 5 by 5 in size. Okay, first question. What's the volume of this cube? The answer is 125. How'd you get it? 5 times 5 times 5 is 125. So this thing has a volume of 125 cubic units. Okay. Now I took a cube. Well, one other question. What's the surface area of this cube? Say louder. 150. How'd you calculate it? Each side has a surface area of 5 times 5, or 25. And how many sides does a cube have? 6. So 6 sides, 25 square units per side equals 150. So the surface area of this big cube, small big cube, is 150. The volume was 125. I took a cube identical to this one, and I cut it up into smaller cubes, each one of which is, you even see that? Is 1 by 1 by 1. Okay, so first question. If I cut up a cube like this, 5 by 5 by 5, into 1 by 1 by 1 cubes, how many little cubes did I get? I got 125, right? So what's the volume of each one of these little cubes, 1 by 1 by 1? What's the total volume? It has to be the same as this, right? This had a volume of 125, and the volume of all these little cubes is still 125. Pardon me?
You didn't change the volume by adding it up.
Exactly. I didn't add anything. I didn't subtract anything. What's the surface area? Okay, what's the surface area of one of these little cubes? It's 1 by 1 by 1. No. The surface area of one little cube is 6, right? Each side is 1 times 1. There's 6 sides, so the surface area of each one of the little cubes is 6. What's the total surface area? 6 times 125. You can use your phone. It's 750. So do you see what just happened? The same volume of material, 125 cubic units, 125 cubic units, surface area 150, surface area 750. So I multiplied the surface area by 5 simply by dividing up this cube into smaller pieces. And you can imagine, I think, that if I, with a scalpel and a microscope, cut each of these up, I could keep on multiplying the surface area with the same volume of material, a long way. That's why having really, really small particles is so important, because taking a big hunk of rock and dividing it up into particles of dust 1,000th of an inch in diameter vastly multiplies the surface area with the same amount of material, which is why this argillic layer has so much surface area, because it's made up of tiny, tiny particles that have been accumulated there. And surface is so important. It's where everything happens. That's why this layer is crucial ecologically. And by the way, remember these? This is the cup that had the bouillon cube in it. And I don't know if you can see, but the bouillon cube is still there, mostly solid, and the water has turned a very slightly, tinted shade of orange. This is the powder. I can smell the beef. You see the difference between the two things? The powder has dissolved to a much greater extent than the cube has. Same volume of material. The powder, because it's in tiny, tiny pieces relative to the size of the bouillon cube, has much more surface area. And so it can react with the water much faster to a much greater extent. And in fact, it's largely dissolved in the water, and the cube is still mostly solid because it has so much less surface area for the water and the cube to interact. So surface area is really important ecologically. So this layer is really, really crucial. Now, why does it form layers? And this is coming back to your question. We're going to perform a thought experiment together. I'm going to give you an analogy, okay? Something I'd like you to imagine. Imagine a little stream flowing down a gentle slope in a forest, okay? Little stream. The stream is full of rocks. And so there are places where the rocks are just below the surface and the water flows over the rocks. There are places where the rocks are big enough that they crack the surface and the water flows around the rocks in those places. There's a path paralleling the stream. And I walk up the path, upstream, uphill, carrying two things. And I get to a point, put down my burden, pick up one of the two things I've carried, which is a very large basket of dead leaves that I've collected from the trees in the forest around. And I dump the basket of dead leaves into the stream. Little stream flowing downhill, full of rocks. And of course, the leaves, are floating in the water and start being carried by the water downstream, downhill. I run down the path way faster than the stream is flowing, get to a place well downstream, and I park myself and I'm watching the stream. I want to see leaves go by. Okay, so small stream flowing downhill, lots and lots of rocks in it, dumped a bushel basket full of dead leaves into it. I've run downstream. I want to see whether any leaves float by. How many of you think I'm going to see a whole bunch of leaves float by because I dumped a whole bunch of leaves upstream? Raise your hand. How many think that I'm not going to see any leaves flow by? Raise your hand. How many don't know? That's everybody else. Well, the fact is, if I've gone far enough downstream, I'm probably not going to see any leaves, or I'm going to see very few. Because think about what's happened to the leaves floating on the water in this little stream that's full of rocks. What's happened to most of those leaves as they have flowed down? Absolutely. I mean, if the rocks were a little below the surface and the water was flowing over them, so the leaf gets carried onto the rock, maybe it sticks and the water isn't flowing hard enough to push the leaf off. If the rock breaks the surface and the water's flowing around it, so probably leaves that are floating in the water get trapped behind the rocks. And so if there's a lot of rocks in that stream, and I've gone well downstream, most of the leaves are going to get caught on rocks in the stream. I go back up to my starting point, uphill, upstream. I carried two things. The second thing I carried was a big jug of brightly colored, highly concentrated, non-toxic, biodegradable, non-GMO dye. Let's say it was bright orange dye. And I dumped a big jug of bright orange dye into the stream. And I run downhill to where I was before, park myself, and I wait to see if I'm going to get orange water. Am I going to get orange water?
Yeah,
I am. Why?
because it's carried by the water. It's not gonna get stuck in anything if it's not solid.
It's not going to get stuck in anything. What actually happens to the dye in the water? It dissolves in the water. The dye, the leaves float on the water. The dye becomes part of the water. So if the water flows over a submerged rock, the dyed water flows over the submerged rock. If water flows around an exposed rock, the dyed water flows around the exposed rock. I mean, yes, it's going to get diluted by the volume of water, but if it was nice and bright and highly concentrated, I'm still going to see dyed water, even if I run well downstream. The clay particles, the dust that forms the argillic layer, is tiny, a thousandth of an inch in diameter, but it's thousands of times bigger than calcium atoms that form the calcic layer. The clay particles, tiny as they are, don't get dissolved in the water. They get suspended in it, which means as rainwater, dust blows in, and the dust brings in clay particles and elements, trace elements like calcium. So then it rains like crazy, and the rainwater begins to percolate into the ground, and it's carrying whatever was on the surface, like the dust and the trace elements. But the clay particles aren't dissolved in the water, they're suspended, and as they get into the ground, they start running into stuff that's already in the ground, just like the rocks in the stream, and they get caught. The calcium atoms and other trace elements, which are so much smaller, dissolve in the water. So if the water can keep flowing around the stuff that's already in the ground and get deeper, those trace elements get carried with the water as deeply as the water can get until the water evaporates. And so the result is the clay particles get trapped closer to the surface than the calcium atoms and other trace elements, which get carried deeper with the water. And the result of that difference in size, basically, is I get layers or horizons forming in well-developed soil. Okay. Okay. Now, I told you earlier that there were two alternatives for the top layer of soil. Of course, by far the most common one is that stuff starts growing. Big stuff. Stuff you can see, the stuff, the trees, the things we notice, the saguaros, the wildflowers, et cetera, and really that sets up a very interesting dynamic in any ecosystem, including the desert. The composition of the soil, what nutrients it has, how well developed that clay layer, that argillic layer is, the trace elements, its consistency. Is it sandy? Is it clayey? Is it, and also things like its elevation and what, is it north slope or south slope, stuff like that. But fundamentally, the soil itself determines what can live on it, what can grow on it, what plants exist there. And of course, the plants, to a significant extent, determine the animals that can be in that area as well. So the soil shapes the rest of the ecosystem. But in turn, the living things in the ecosystem, the biota, as they grow, die, urinate, defecate, lay eggs, et cetera, and all that stuff decays, that returns nutrients, minerals, trace elements, carbon compounds back into the soil. So the soil isn't a one-time thing. It doesn't just get formed and boom, it's done. It's constantly being formed and reformed due to the things that are living on it. And the soil can be refreshed if properly tended by the living things on it. And by the way, this is a reason why we get so concerned about non-native plants in some cases. I'm sure you're familiar with the concern. Non-native plants that have often been brought here for good reasons, but have unintended consequences. Namely, they outcompete native plants in many cases. Nothing here is adapted yet to eat them, for example. So, they proliferate and they can crowd out the native stuff, and they do really quite well. And that includes things that used to be ornamentals, like fountain grass. If you have any fountain grass, get rid of it, please. But think about, there's another implication. We worry about non-native grass for a couple of reasons. The things you hear about are, well, it's displacing the native material. Yeah, that's true, but remember, everything was once non-native. Nothing magically appeared here or was here since time immemorial. Everything has come here from somewhere. It just happened a long time ago, typically. Non-natives are more recent arrivals. The bigger issue is that because the non-natives tend to be denser and oilier, they're a much more significant fire risk here than most of our native vegetation is. So that's a real concern. There's another thing that happens though. Think about it. Think about the soil in an area that for thousands of years has supported a natural Sonoran Desert ecosystem with the plants and animals that we normally see here. And now the plants all get displaced by non-natives that often grow ineffectively as monocultures. Really, it's pretty much the only thing there. So the animals change because their food source is gone, and they haven't yet adapted in many cases to eating the non-native stuff. The non-native stuff grows and dies and decays, and its chemicals, the things that make up the non-natives, go back into the soil. Rain carries it into the soil. But those chemicals in non-native plants often are somewhat different than the chemicals in native plants. And what that means is that if the non-natives are allowed to grow and die and decay for long enough periods of time, that process will actually change the soil, change the chemical composition of the soil in a way that, guess what, favors the continued growth of the non-native plants because they are adapted to it.
Again, we just talked about what invasives, how they can change the soil. You said something earlier in which you talked about pollutants, either pollutants that industry creates or that come from China or wherever. Is there any information about whether or not those are also changing the soil for better or for ill, thousands of miles away?
Or here. The question was, are pollutants of various kinds also changing the soil? And the answer is absolutely. I mean, we have here in Phoenix, we have Superfund sites from old semiconductor manufacturing, which put what turned out to be, nobody intended to poison the soil. but they turned out to be toxic, didn't break down very fast, and eventually percolated into groundwater. So absolutely, pollution is another way that the composition of soil can be changed in ways that are no longer conducive for the growth or even the restoration, in some cases, of native plants. So it's one of the reasons why we're so concerned about non-native plants and, of course, pollution in general. Pollution, we've got more of a handle on. I mean, there's a lot of laws and regulations and Superfund cleanups and stuff like that. We get it, especially when when your drinking water is a weird color or tastes bad or causes cancer. We kind of get that. Non-native plants are not yet as well controlled, sadly, as pollution is. Okay, there is another alternative to the top layer of soil. It's much less common, much less common. It's called desert pavement. And you may never have seen this. There are few places in the preserve I'm aware of where you can see patches of this, but fortunately it doesn't occur very often. But this is what it looks like. And that coin, can you see that's a quarter. So what characterizes these areas are they're usually flat or close to flat, level, and the surface seems to be covered with a layer of interlocked pebbles of, kind of generally the same size class. They're not exactly the same size, obviously, but there's very few big boulders. They're kind of these small to medium-sized rocks. And if you touch it, you'll find out that these pebbles are kind of interlocked with each other. They don't move very much. There's some disagreement about exactly how this stuff forms, but here's kind of the current thinking. Soil, as I've described, has the structure of layers, and dirt typically doesn't. Rock fragments typically don't have much structure to them, but there is one exception, which is that water, for example, will carry different size rocks different distances. Wind will carry different size rocks different distances. Heavy stuff doesn't go as far as light stuff does. And so often rocks, dirt of various sizes, can get kind of sorted by size. And often we find the desert pavement on a gentle slope of a foothill that's come off of a steeper slope nearby. And so the foothills around, for example, the McDowell Mountains or any mountains may be places to find this stuff. And imagine that you're on the gentle part of the foothills around a mountain range, and there's a little depression in that slope. And over thousands of years, pebbles have been carried by water, by wind, by gravity, different distances from the mountain. And so I get an accumulation of pebbles of, roughly the same size in one of these depressions. They don't go any further because they're trapped, in the depression in the ground. So I have a collection over an extended area of rocks of similar size. Over thousands of years, guess what? Wind-borne dust gets blown in again and again and again. And rain carries the very, very tiny particles of clayey dust down between the small rocks to eventually begin to accumulate as a layer of clayey material, kind of like the argillic layer in soil, but here it's underneath an existing layer of pebbles. So there's kind of a surface, a cover over it, as opposed to being exposed completely to the air and water. And remember, the clay, as it accumulates into an actual layer of clay underneath these rocks, does a couple things. First of all, the layer of clay that's accumulating over time actually lifts the rocks off the ground. So now we have a layer of rocks over a layer of clay. And as the clay continues to get wet, remember what happens to clay when it gets wet. Not only is it slippery, it expands. And as the clay expands and contracts, it jostles the rocks that are lying on top of it, so that over thousands of years, tens of thousands of years, those pebbles begin to interlock with each other. And we end up with a layer of tightly interlocked pebbles on top of a layer of clay. And if you cut into pavement, you can actually see this. The layer of clay is called an AV layer. And then there's a layer of rock on top of it. And water can get through, and the dust particles can probably still get through. But imagine a seed being blown onto this stuff. It germinates, it sends, it's got a little rootlet, and that little rootlet is trying to get into the ground and get to water and nutrients. And it runs into a nice, tightly interlocked layer of pebbles. And so we end up with an area where nothing very big is growing, unless something, whether it's a footprint or something else, breaks apart that layer of interlocked pebbles at the surface. So we see this extended layer where it may be surrounded by shrubs or trees, and there's nothing in that layer. Again, not very common, but it's interesting if and when you see it. Now, one thing I do want to make clear, we're just about at the end here, is we have a tendency to think about life in the form of things we can see, big, visible stuff, plants and animals. It turns out that life on Earth is ubiquitous. I mean, there's life everywhere scientists have looked. There's things living 10,000 feet down in diamond mines. There's things living in glaciers in Antarctica. There's things living at the tops of mountains. There's things living in the thermal pools at Yellowstone, under conditions that 50 years ago, biologists would have said were impossible to support life. There's life everywhere, mostly invisible to the naked eye. It's mostly microbial life. So bedrock, exposed bedrock, has life on it. Now, some of it's quite visible. We see lichen, we see varnish. Varnish, by the way, has a biological component. Come to the other lecture, and you'll learn more about that. Moss sometimes, but more than anything else, there's bacteria all over rock surfaces. Dirt, fragments of rock. We have microbes, we have lichen, we have varnish, if it's, if these are big enough. We have mosses. We also may have biological soil crust that grows directly on dirt, not on soil. It enriches the dirt. And over time, biological soil crust, which we also talk about in a different lecture, can help turn the dirt into soil. Finally, we get to soil that we're familiar with. And of course, we see the big things, but even that pavement, which doesn't have anything very visible growing on it, is covered with microbial life. So one thing to keep in mind when you think about the ecosystem is most of the ecosystem is in fact invisible to us. It's either microbial and or it's underground in the form of fungus and subterranean animals, ants and various things. So much of the ecosystem is completely invisible. And don't think that if you can't see it, it's not there, because it is. Okay. We're done. You now understand the ecology of desert dirt, from rock to soil to living things. It really isn't very complicated, but this is, again, the fundamental basis for not only this ecosystem, but every ecosystem on Earth. And it's kind of nice to understand a little bit about that foundational element. There are lots of opportunities to learn more. I encourage you to go to the website of the McDowell Sonoran Conservancy, which is mcdowellsonoran.org, and look at events. If you'd like to volunteer, there's a volunteer tab, and of course, there's a very big donate button, very, very visible. And I hope that you'll maybe look around your neighborhood a little bit differently than you have before, and not only notice the trees and the flowers and the interesting big rock formations, but take a look at the dirt as well. So come play with us. There's all kinds of stuff to do. I do want to, in the interest of full disclosure and complete honesty, tell you that I am not an expert on any of the things that I've told you. However, this stuff has been reviewed by a lot of people who really are experts, and they have said it's okay. So I am hopeful and reasonably confident that my fibs were small and they were white lies and nothing fundamental. If any of you would like to learn more, there's a bibliography, and this presentation I think is on the website, the Conservancy's website, and there's stuff being published all the time. And if you go to Google Scholar, or if you have access to a library at one of the universities, for example, you'll find hundreds and hundreds of papers and articles that are more recent than this list, but this list is a place to start. And I'd encourage you, it's really interesting to get into it. Thank you.